Physics 124, instrumentation, optics, instrumentation, laboratory, concept 3. I'm assuming at this point you're able to start the software and you're able to get, open the file and get this picture on your screen. The way you got the ray traces is you went up to ray trace and you hit trace and render, and that's how you did that. If you want to get rid of them, you can do ray trace and then hit the trace all sources. I don't know why that destroys it, but that's one way of getting rid of them if you don't want them for some reason. So what I wanted you to do for the lab, this is going to be very simple. Trace and render. As you noted before, you got 3 colors coming out of here. They're all practically coming out of the exact same spot. They go through the lens, and the only thing that gets through is the yellow. So what are we going to do? What do I want you to do? I want you to take the hole in this plate and I want you to enlarge it. And I don't care how much you enlarge it. You got like, I don't know, this plate's maybe like 300 millimeters high. You can enlarge that hole to 20, 50, 10, 3, any size, and you will see that all of this will get through. So what I want you to do is enlarge in the hole, do the trace, go up to ray trace and do a trace and render after you enlarge the hole, and take a picture. You can take a picture a number of ways. You could either use the snipping tool, which is usually found on the bottom of your ribbon here, like this. You click this and you get a little dialog box, and you can go like this and take a picture, and you can, that's one way of doing it, and you can drop that on your document. The other way is just take your cell phone and literally take a picture of the screen and put that on your document. And then there's another way. If you look around at these icons here, view all, that's a very handy. Next to that is the save as a JPEG. If you click that, that'll take the screen here, and then it'll save it, and you can put it in whatever folder you want to put it. Okay, so you have different ways of saving a picture and putting it on a document. So I'll show you how to increase the size of the hole in this plate. And remember I said that, just kind of roll around. Remember I said this is a plate with the smallest of holes in it. This is a lens, an ideal lens. No lens is perfectly thin like this. That's ridiculous. So this is only for concept. This is for the concept of an invention. In this software, you can literally load actual real lenses, and they will behave exactly the way they're supposed to. And to be able to get a focus super sharp, you would have to compound lenses, follow one after another, to compensate for the weakness of each lens. No lens is perfect. So this is really only to demonstrate the concept. You could use this software though to actually do real engineering with real lenses with real specifications, and you could really determine how small of a focal point can you get. You can't get an infinitely small focal point, not with lenses. Here, with an ideal lens, yes we can, but not in a real lens. So if you were to engineer, you could start like this if you're an engineer, but then you'd have to start working, incorporating real parts into it and finding out what you really can and cannot do. Also, too, this plate's also infinitely thin too. There's no infinitely thin plate that you're going to find. Okay. So how do we enlarge the hole here? So you're going to enlarge the hole. You're going to do a ray trace, and then you're going to show me all the beams got through. You're going to pick a nice angle, and you're going to take a picture, and I'll see that oh yeah, all 3 colors got through there. Okay. So how are you going to do that? Well, over on this side, it shows the, if you double click on the folder that says Optical, here are your 3 point sources that I created. If you double click on the geometry folder, there's everything that's in there. There's this plate with end-sided hole, that's this thing, the ideal lens, And then that sphere that I was using that you can't see because it's so small, that's the actual, that's the bacteria. This is, and you double click the analysis, and that's this thing over here. So that can tell you how many watts of power and it can tell you the wavelength, and it can tell you whatever is hitting it from these sources. So you're going to go to the plate with the n-sided hole. That's this plate here. That's what you're going to modify. Okay. When you double click it, this is the size of the hole. 4-E. That's you look at the drawing here. That's the number you're going to change. This number right there. So right now it's 1 millimeter to the -5th power. Just get rid of that and change it to a 10 or a 20 or 30 or 5 or something. Change it to something else. Then hit your apply and your OK and close it. Okay, after you change it. Okay, I'm not going to do it. You're going to do this. Okay, so you're only changing the hole, this hole in here. That's what you're changing. It's actually a hexagon. Okay, and then you're going to go back up to ray trace, trace and render, and show me a picture how you can show me the picture from this viewpoint. You can zoom in here, you can zoom here, you can find an interesting angle, however you want to do it. You're just demonstrating that you did change something. Okay. Then the other thing that you'll put in this, in terms of pictures, in this in your report, is I want you to put 2 pictures of the same thing. You're gonna have to go online or somewhere or in a book. Find a picture of the component of a cell or something microscopic that's a non-focal microscope picture, and the same item but in a confocal microscope with the confocal microscope. So you can compare. So just to compare and contrast, you can see the difference between how this technology has so radically affected. So you'll be 3 pictures on the lab. Just this, what do you do here, and then what you can find, and then you'll explain to me 2 things. You'll explain to me, you want to call this an introduction? Fine. Explain to me the broad principle of how this works. It's only a few sentences. Okay, you have a pinhole in a lens. You tell me how it works. Just broad principle. And then you're going to give me a specific principle. This requires you to do some work because you're a biology student, you're interested, you probably are curious about the instrumentation that you use. So you're going to tell me, what you're going to tell me is in a modern confocal microscope, if this is the sample, that's the sample, right? That's the thing that we're probing. This is the thing that's of interest to us. That little microbe right there. What you're going to tell me is how do they, let's see if I can get it back into the picture. Probably can't. How do they do the scans? How do they scan and then come over and scan again and come over? How do they do it? Remember in the original patent, they're literally putting the thing on a slide and shaking the slide in a fashion like this to create a raster. And then if you want to go a deeper one, then you have to go deeper. So how do they do it in a modern confocal microscope? And I believe there are different ways that they do it, different manufacturers, different technologies. So I just want you to tell me in a few words. You can cite an example. You may find that there's more than one way to do it, but I just want you to tell me in a modern way, how do they do it? So that's basically your report. It should be interesting to you if you're a biology person and you've been using this equipment and you just want to understand it better. No math in this one, just some pictures and some writing. I'll put it on the score sheet, what I just told you. You guys have a great summer.